Okay, so what I'd like to do is start looking at vectors. Okay, so if I can find my vectors, here we go. So, and some of you might have more experience with vectors than others. And so I'm going to kind of go under the assumption that you know nothing about vectors. But I know that's not true. I know you know some things about vectors. So, some of this you might be able to fast forward. Some of it you might be, oh yeah, I know this. The thing is too, you might know it, but the notation might be different too. And so that's a bit of what this is about in terms of like just learning what is the notation. Maybe it's a little bit different than physics, but really a vector, if you think about like a vector, a good definition, there's two components. It's a directed line segment. And so there are two pieces to that. One is the fact that it's directed, meaning there's a definite direction. That arrow is important. And segment, meaning there's also a distance. So like there's a direction and a distance. Like those would also be important things to, make sure to know that there's a direction and a distance. Now, from a geometry point of view, it's a little bit deceiving or incorrect to see this, which has an arrow, and call that a segment. Because we know in geometry that's not a segment, that's a ray. But here, that arrow doesn't refer to that it goes on forever. It refers to which direction are you pointing. But it is definitely a finite length. It is a segment in terms of its distance. And so the first couple problems here are just like basic vector problems, like how do you add two vectors? Like how do you add vector v plus vector w? Well, one thing I like to talk about is tip to tail. So you would put the tip, which is like the beginning of a vector, to the tail of the other vector. So if I wanted to add v plus w, what I could do, this guy here, is I just want to copy v here so I have a good representation of it. So I could take v, so here's vector v, and then I could add to it vector w, which is this guy, and I would just simply put him on the end. So v, w, and the sum would be like starting at the starting point of the first vector and going to the ending point of the last vector. So if I started here and went up v and out w, I could have just gone directly there. So the green segment, wherever I want to put, wherever I want to put this segment here, that is v plus w. Okay, so that's just, again, just simple adding two vectors. And you could do scale multiples of them, so 3 w's minus v. So again, I can go ahead and take, let's go ahead and erase this so we can lasso that on my tablet. Awesome. Okay, so what I want to do is then maybe just like, here's the w. So maybe I want to go over here and I want to have 3 of those. So I could just copy it. Oops, I should probably just paste, clone it. There's 1. And then clone that again, 2. So I have 1, 2, 3w. Right? So going 3w. And it says go minus v. Well, if v is pointing up into the right, then a minus v would be down and to the left. So I could just simply go in the reverse direction. We go here, down. I can grab that guy, and that's my minus v. So again, going over 3w minus v, and then my actual answer, my vector, would be from the start of here to the end of there. So again, it has a certain length and it has a certain direction, going from top down to bottom. Okay, now those are just kind of just in space, right, or on the plane, I should say, with no relative positioning. Now we're going to talk about a position vector. So notice that these vectors are on a grid, and I've got 5 of them. And when I start looking at these vectors, there's going to be 2 components. There's going to be a horizontal component and a vertical component. In the horizontal component, we're going to associate with the letter I. the vertical component with a j. And it gets a bit confusing. You're going to be careful because we just got out of complex plane and we just got out of imaginary numbers and we had i's there. Here, we're representing ij as just letters of vectors. And in fact, if you do like a third dimension, which we will, you'd have the vector k. The horizontal direction is in terms of I, the vertical direction is in terms of j. So if I look at this first vector, v1, there are 0 components going to the left or the right. So I'd have 0i. So v1 would be 0i. Whoops, I'm saying 0i. I wrote 0j, my bad. v1. So 0i, but I'm going down to j. So that's one way to show position of vector. For wherever you start, you're going to go straight down 2 units. Okay, vector 2 starts here, goes over 1, 2, 3, 4, 5, 6, 7, and up 1, 2, 3, 4, 5, 6, 7, 8, 9. So I could call vector 2 7i plus 9j. Okay, vector 3. It's 1, 2, 3, 4. It's 4 to the right, but nothing up or down. So it'd be 0j. Vector 4, notice it's kind of going backwards. So 1, 2, 3, 4, 5, 6, down 2. So vector 4 could be negative 6i minus 2j. And then vector 5 is completely to the left. So 1, 2, 3, 4, 5, 6, 7, 8. So vector 5 is negative 8i plus 0j. Now, do you have to put in like the zeros? Not at all. So if you don't want to put the 0j here, or you don't want to put the 0i there, or the 0j there, that's fine too. It's just under the assumption if it's not there, it'd be 0 in that value. Okay, so another way that we could use vectors is to represent forces. And so, because the force would have a certain strength or a certain magnitude, and you might be pulling or pushing or exerting that force in a certain direction. So a vector makes a great visual representation of that force, which is why we use them in physics and we'll use them in calculus. And so again, assuming you know nothing about that, we're kind of just using them as models here. So it says find the resultant force in each set of vectors. So a resultant force, you're not doing tip to tail like we did before. You are applying 2 different forces to the same point. And so like if I think about this, there's a point here. So if I exert force, looks like force 2 in this direction with a certain strength, and that strength is based on how large that is, based on these, the components. And I pull the point in this direction as well. So they're both going in opposite directions. Like it's going to probably end up somewhere in the middle. Some of these forces will cancel out. So a good way to think about that is to break down your 2 forces into component form, which would be the i's and the j's. So vector F2 is 1, 2, 3, 4, 5, 6. So it's 6i and 0j's. And then F1 is 1, 2, 3, 1, 2, negative 3i plus 2j. So when they act simultaneously, some of these are going to cancel each other out. So if I just add up the components, 3i plus 2j, so that's sort of like my net overall, that's like my overall force that's going to happen. I'm going to result in 3 to the right and 2 up. 3 to the right and 2 up. So over 3, up 2, right there. So if those 2 forces acted simultaneously, this particle would just basically slide up in that direction. And some of you who've seen vectors before also know that you could have got that by making a parallelogram. So if I just take this distance, this force here, and if I actually do move it over here, notice like that would have been, like where you would have gone. So you could think about it tip to tail, but these are acting simultaneously. And then, just to complete our parallelogram, why not? Right? It's Friday. Complete our parallelogram. So there we go. So a resultant force, and there's only 2, could also be the diagonal of the parallelogram. Well, now when you start getting more than two forces, you don't have a parallelogram anymore. You could add up the components, kind of see where it goes. So I might first represent this by looking at F1. So F1 goes over 2 and up 1, 2, 3, 4. So 2i plus 4j. Vector 2, 1, 2, 3, 4, 5, 6, 7 is just negative 7i, no j's. And then our third force, our third vector, is represented 1, 2, 3, down 2. 3i minus 2j. So when I add up all those components, 2 minus 7 plus 3 should be negative 2i, and then 4 minus 2 is positive 2j. I think I did the math right. If I didn't, send me an email. I'll fix it. So overall, this point, if there was a particle there, its net change would be to the left 2 and up 2. To the left 2 and up 2 to the point right there. So I draw in, and that right there would represent that particular, vector. I'm going to make it a little thicker here to show it's up here. And there it is. Okay. Now, let's talk about maybe unit vectors next. So a unit vector, kind of like in the unit circle, the unit vector has a magnitude or a length of 1. And maybe before we talk about having a magnitude of 1, we should also figure out how do we find magnitude. So I'm going to go a little bit out of order here. I'm going to actually give you a definition of magnitude. Magnitude would be the length or the distance of a segment. Of that vector. So our magnitude is the length of the vector. And you probably have an intuitive way to find this. So like if you know you have this vector here, and you know that it can be broken down into its components of how much do you go to the right and how much do you go up, then I'm hoping you see, drum roll please, the Pythagorean theorem, right? So it's this component plus this component squared is this component squared. So it's exactly the Pythagorean theorem. And so if you want to know what is the notation, like how do I indicate that you are trying to find magnitude, you would use a double set, almost as like absolute value, right? So when you see this symbol here, that means find the magnitude. And again, thinking about it could be like the square root of a squared plus b squared square rooted. So if I went over in this direction A, up this direction B, then the magnitude of this vector would be the result of that. And notice that this no longer is going to have any component forms, because vector v could have had a components of I and b components of j. So that's a vector. But this right here is an actual just number. So we sometimes would call that a scalar. A scalar has no vector components, And the other thing too is that it's going to be a positive number. So it does represent distance. Okay, so if again, thinking about magnitude, I thought I had an example of looking for magnitude, but I know I have a unit vector. So let's go back to that section for a second here. And so it's, a unit vector by definition is a vector with magnitude 1. Vector with magnitude 1. And the thing is that 1 could represent any unit. It could be 1 mile. It could be 1 inch. It could be 1 Newton if it represents force. I mean, like, its magnitude, whatever it represents, it is 1 unit in that particular problem. So right now, I'm getting a little excited here because I see one of my favorite triangle triples. But if I were to draw out V, I would say, okay, wherever V starts, I would go left 5 and up 12. So left 5, up 12. So here's what vector V looks like. There's V. And I know that I can complete the Pythagorean theorem. The magnitude of V would equal the square root of -5 squared plus 12 squared, which I know would be 25 plus 144, which is 169. Square root is 13. Or I could remember from my geometry days, it's a 5, 12, 13 triangle. Okay, so the magnitude is 13. So that is clearly not a unit vector. I would want that value to be 1. So what I'm going to do is I'm going to take that 13 and scale it down to 1. And the easiest way to scale it down is to divide by 13, because 13 divided by 13 would be 1. Okay, well, it's not, you can't just decide, hey, I'm going to divide by 13 unless I divide everything by 13. So if I would have divided this by 13, because 13 over 13 is equal to 1, well, that means I'd have to divide this by 13 and this by 13. And so if I divide all of those by 13, in essence, what I'm doing is I'm creating just a tiny but still similar triangle right there. So there would be like 1/13 of the whole thing. And so if once you find the existing magnitude, to keep that same direction, you just scale it down. So then my answer would be 1/13 of negative 5i plus 12j. And again, just to kind of emphasize, this is a vector. This right here is a scalar. It's a scale factor. So if I do 1/13 of this, so that would be negative 5/13 I plus 12/13 j. That would be my unit vector in the same direction as v. And again, think about that same direction, going left this amount and up this amount keeps that same slope or keeps that same scale factor. Okay, so let's go ahead and just do one more here, and then maybe it'd be a good stop to end the video and take a break, and then we'll do another video on the rest of the notes. So 7 and negative 24. So again, I'm anticipating a great triangle. I'm going to go to the right 7 and down 24. So over 7 and then down 24. So this one, is a 7, 24, 25 triangle right there. So if W represents the vector, I knew that the magnitude of W was 25. And again, I could get that from the Pythagorean theorem. 7 squared plus negative 24 squared would be the magnitude of W. Now, clearly, 25 is not 1. And if I want it to be a unit vector, I'd have to divide that by 25. So if I divide that by 25, I would get 1. So if this was 25, and I divide it by 25 to get 1, then I divide this by 25, and I divide that by 25. So we're scaling them all down by 25. So then I could write my final answer in vector, a unit vector in the direction of W is equal to 7 over 24 I minus 24 over 25j. Now, I was just so excited to be done with that problem, and then I realized after rereading it, it says in the opposite direction. So maybe you already caught that, but I just saw it now. The opposite direction is very easy to do. Opposite direction just means that I want to go, instead of going down into the right, I want to go up. Oops. I want to go up into the left. So I want to go up into the left in that direction. So just flip the signs. So we'll go red. So in the opposite direction, so W in the opposite direction, I guess, could be negative 7 24ths I plus 20. Oh, wow. Another mistake there. There should be negative 7 25ths. Wow. Definitely not doing good. No bueno for me. Let's fix that. And fix that. Okay, so this should be negative 7 25ths I plus 24 25ths j. And then coming back, I suppose doesn't have to be the exact color, but it's nice to match. 7 25ths. Okay, so that's the unit vector in the direction of W. This is in the opposite direction, but still a unit vector, because if you did the Pythagorean theorem, you'd get a value equal to 1. Okay, so again, some of this you might know, it might seem familiar. Some of it might just be a different notation. But I'll go ahead and finish the notes in the next video, or maybe 2 videos, we'll see. And then, we'll just keep working on the homework. Oops. And